It was described by Prime Minister Pedro Sanchez as the biggest natural disaster in Spain's recent history. And this was no understatement. If you had to think of the most defining natural disasters of the last year, I'm guessing that the Valencia floods would come close to the top of that list. The Valencia floods resulted in the deaths of over 200 people, with thousands more left injured or missing. In just over 8 hours, Valencia, the Balearic Islands, and Castilla-La Mancha experienced a year's worth of rainfall, which tore through the city and surrounding towns as deadly flash floods. One victim said that their life had turned to dust. The water was strong enough to sweep cars onto the streets, tear homes to pieces, and drag tons of sediment out to sea. This disaster came at a really key moment, right before nations would come together at the 29th Conference of the Parties, or COP29, in Baku, Azerbaijan, to try and come to an agreement for managing the future of climate change. People hoped that what had happened in Valencia would be a sobering backdrop to the climate debates, highlighting the sense of urgency for change in a landscape that's experiencing more frequent and unpredictable weather events. But the reality was a bit less inspiring, as COP29 didn't agree on any specific timeline in its goal to move away from carbon emissions, even though this is vital for the prevention aspect of managing flood risk. With this disappointment, many scientists have been left to wonder whether flooding of the scale and unpredictability witnessed in Valencia would become our new normal. It was a volatile mix of conditions that converged in the Spanish atmosphere on the 29th of October, leading to unprecedented and disastrous levels of rainfall. But why and how did those floods happen in the first place? I'm James Stewart and you're watching Astrum Earth. In this video, we'll investigate exactly what these conditions were and how they came together to cause devastation on the streets of Valencia. In the aftermath of the Valencia floods, news stories have covered the great human cost, the dedication of thousands of cleanup volunteers, and the community's outrage at authorities for failing to do more. In this video, we'll put the record straight, outlining some of the mistakes that were made and the efforts to rebuild. To better understand the Valencia storm, it's worth zooming out and analysing thunderstorms more generally. Thunderstorms are an example of a convective process, that is, they are fueled by convection. It's simply a form of energy transfer where warmer, less dense material rises and cooler, denser material sinks. What does this mean for weather systems though? Well, the sun heats water at the surface of the ocean, causing it to evaporate and rise into the atmosphere due to its relatively low density. The more this water vapour rises, the cooler it gets, until it reaches the condensation level, where it condenses to form precipitation, or it turns into rain. Above this condensation level is the 0-degree isotherm, where it's so cold that the rain would freeze and become snow or hail. This means there are two invisible lines in the atmosphere, and the space between them is where clouds form. If thunderclouds become heavy enough with condensed water vapour, they'll release the water in a precipitation event. These processes are a key part of the water cycle, which moves water between the land, ocean and atmosphere, and across different physical states. Since the total amount of water available on Earth remains constant, we need the water cycle to make fresh water continually available for us to drink. And it's not only us that need this. The water cycle has helped sustain life on Earth throughout its history. It's amazing to think that your next glass of water contains the same water molecules that once quenched the thirst of dinosaurs. So this is why clouds form, but how and when does it happen at the scale and intensity we saw in Valencia? To visualise what the European atmosphere looks like, meteorologists often use synoptic weather maps, which give an overview of all the wind patterns, atmospheric pressure systems, and currents in a particular area. You may already know that the Earth has several major circulating currents, or cells, which distribute heat around the world. These are the polar cells, the Hadley cells at the equator, and the Ferrel cells in between. These cells, like clouds, are driven by convection, but on a larger scale. Wherever you get warm air rising, this creates an area of low pressure. In these areas you typically see more cloud, precipitation and unsettled weather. If the low pressure is extreme enough, you may even get tropical cyclones. But as the name suggests, these happen mostly in the tropics. In contrast, high pressure areas are created when cooler air sinks back towards the Earth's surface, bringing clearer weather conditions and low winds. Since these conditions are so different to the weather caused by cyclones, high pressure systems are aptly named anticyclones. Although areas of high and low pressure are constantly changing, some can become more permanent. In fact, there is a large semi-permanent anticyclone found on the Azores archipelago, which is close enough to Spain to play a key role in influencing its weather. 3 days before the disaster in Valencia, something started building in the atmosphere. Spanish meteorologists categorised the October storm as a Jana storm, which translated means isolated depression at high levels. Remember, areas of low pressure, also known as depressions, bring unsettled weather and rain to affected areas. And in this case, the cause of the depression was a cut-off low. Cut-off lows are high-altitude, low-pressure weather systems that become isolated from the polar jet stream, a core of strong eastward-blowing winds found 5 to 7 miles above the Earth's surface, at the boundary between the northern hemisphere's feral and polar cells. If any of this cold polar air becomes isolated from the rest of the jet stream, it can move independently. It becomes a renegade cold drop, or gota fría, as the Spanish call it. But a cold drop doesn't cause extreme weather unless it moves through an area where there is a high temperature difference between itself and the surroundings. If we think back to the time of the storm, it was autumn. The Mediterranean Sea had just been heated by the sun all through the summer, and it had a pretty high temperature. It was this high temperature that meant warm, moist air could evaporate from the Mediterranean and Balearic Seas and combine with hot, dry currents of air from the Sahara, eventually rising up towards the cut-off low. When the rising air reached the cut-off low, warm and cold air collided to kickstart convection, causing rapid condensation so that several low, cohesive thunderclouds were formed. It was the suddenness and magnitude of this condensation in the atmosphere over Valencia which contributed to the intensity of the storm to come. Jana storms are pretty common in southeastern Spain, and the region actually has a reputation for irregular rainfall compared to the rest of the country. Southeastern Spain, which includes the provinces of Valencia, Murcia and Alicante, has a semi-arid climate, where long stretches of little to no rainfall are punctuated by intense precipitation events. The Iberian Peninsula sits at the intersection of the humid North Atlantic region, where storms are common, and a stretch of the subtropical high pressure belt which is very dry. The Azores anticyclone we mentioned earlier is also nearby and comes into play here as well. A key thing you need to know? Well, areas of high and low pressure don't mix easily. High pressure areas like the subtropical high pressure belt and the Azores anticyclone often create a barrier against the rising air from low pressure zones, blocking its path and causing it to get stuck above certain areas. This is what happens to renegade cold drops in the Iberian Peninsula. The longer they stay isolated and stuck in one place, the more time there is for them to collide with warm air rising from the Mediterranean Sea. So Jana storms are more likely to form. And since the cold drop in October spent 3 whole days stuck over Valencia at a time where the ocean was warm, well, what followed seems almost inevitable. Javier Martin and his colleagues set out to investigate how often this happens and reviewed the cases of all torrential rainfall events in southeastern Spain from 1941 to 2017. They found that Jana, the kind of storm that hit Valencia in October, was responsible for over 50% of events. But if Jana storms are relatively common, then why didn't the authorities see this disaster coming? The thing is, not all severe weather events result in natural disasters. So what was it about this Valencia storm that made it so dangerous? Since analysing the storm in more detail, meteorological experts have identified that the storm system had a high CAPE atmosphere, or convective available potential energy. In simpler terms, CAPE is a measure to describe how much energy there is available in the atmosphere to fuel convective processes, like thunderstorms. But why is that important? Well, the more convection there is in a storm system, the more air rises vertically and more potential it has to cool and condense, forming more rain. But how does a storm come to have a high CAPE? Well, the depth of the storm clouds is important here, since more depth allows for more space between those two invisible lines we mentioned earlier, where water remains condensed as rain without evaporating or freezing. The storm clouds over Valencia were intense, not just because they were widespread across the sky, but because they had lots of vertical development, so they towered up to high altitudes in the atmosphere. Another important feature of the storm system was that it persisted over Valencia for an unusually long time without weakening. Easterly winds with a high moisture content from the Mediterranean Ocean were continually blowing towards the storm system, feeding its growth and precipitation throughout the event. The winds of the storm also had a high vertical shear, meaning they increased rapidly in speed as they moved to higher heights in the atmosphere. This caused upward moving currents to tilt as they replaced existing currents in the storm system, creating a strong separation between updrafts and downdrafts in the storm cell. With this separation comes that higher CAPE we talked about, and more convection with it. Since convection is the basis of thunderstorms, it was able to grow stronger and more intense without collapsing. More movement meant more energy, which meant more potential to unleash destruction down on Valencia. Though a high CAPE is a common feature of intense storms, it's not the only thing that makes them intense. Having a high CAPE doesn't count for much unless you also have a high efficiency of precipitation. Rain doesn't always have a clear path to the ground. It could freeze, evaporate, or even blow off course before hitting its target. If rain was 100% efficient, then all the water condensed in the cloud would hit the ground in a rainfall event. Of course, we don't see 100% efficiency in real life, but the Valencia storm had certain features which meant that it came pretty close to reaching its full potential. The cloud bases of the Valencia storm were very low, and there was a high relative humidity in the lower atmosphere, so the rain had little chance to evaporate and only a short distance to fall in order to hit the ground, which maximised its impact. The final and probably most important point is that the storm was quasi-stationary. See, while most storms would rain on a certain area and then blow over, the Valencia storm did not budge. We touched on why this was earlier, because high pressure systems were acting as a barrier and blocking the Jana system from moving beyond the Iberian Peninsula. Since it couldn't blow over, this naturally made the storm more intense for the people affected, as the total rainfall was confined to a much smaller area. Put all of these features together and you get a fiercely intense storm, one capable of making international news and leaving the streets of Valencia unrecognisable. The Valencia storm brought devastation unlike the Spanish had seen in recent history. The town of Turris broke the Spanish record for hourly rainfall at 184.6 millimeters, and the town of Chifa received nearly 500 millimeters of rainfall in 8 hours. To put that into context, the World Meteorological Organization counts heavy rainfall to be anything from 7.6 to 50 millimeters per hour. So the hourly rate of rain that fell in Turris was up to 24 times greater than what we would class as heavy rain. And the result of this heavy rain? In a matter of minutes, tsunami-like floods ripped through the streets of Valencia, trapping people in their homes and vehicles with no hope of immediate rescue. Besides a death toll of over 200 people, the Valencia flooding left a huge impact on people's livelihoods. Valencia's Chamber of Commerce estimated that 48,000 companies have been affected in this disaster. Huge amounts of stock have been damaged by the muddy water, and production has been brought to a standstill. In the aftermath of an event like this, the community has come together in unprecedented numbers to initiate the cleanup operation. Around 50,000 volunteers arrived in the affected areas in the weeks following the disaster, sporting brooms, mops and any other tools necessary to try and bring normality back to the region. But in spite of their desire to help, the volunteers and people of Valencia were angry with authorities for their delay in responding to the floods. During a visit to the area, the King of Spain faced onslaughts of mud and cries of shame from flood victims, who felt the authorities' response was not enough and that flood warnings had been ignored. More recently, a staggering 80,000 protesters gathered on the streets of Valencia on the 29th of December to express their frustration with regional president Carlos Mazon at his poor handling of the event. Why was the authorities' response so poor, and how did this contribute to the impact of the disaster? When you think about management before and after any natural disaster, there are 4 main stages. These are prevention, preparedness, response and recovery. Together they make the disaster management cycle. Valencia is currently in recovery, but the recent protests have prompted people to question just how competent authorities were in the other 3 stages. Arguably the most important part of the response to severe weather is knowing it's coming in the first place and warning the people who are likely to be affected. Unfortunately, this was something the Valencian authorities got badly wrong. The magnitude of the flood was drastically underestimated by early warning systems, and warnings were inefficiently communicated to the public. The National Weather Service issued a red alert for exceptional heavy rains on the morning of Tuesday the 29th of October, but the political authorities of Valencia only sent SMS warnings to the public just after 8 p.m. that evening. By this time, many people, especially in the southern suburbs of the city, had already been hit by deadly floodwaters. Even if warnings had been heeded sooner, the catastrophe of the floods revealed that most people don't know how to properly respond to flooding. Many reacted to warnings by simply going to their garages and trying to move their cars out of harm's way, but this only put them in a trap when the flash floodwaters struck. It's clear that simple warnings are not enough. People must be informed of the predicted impacts of flood events and be trained in the appropriate response well before the flood actually hits. Many people have also argued that Valencia as a city was poorly prepared for the disaster. Recently, rapid urbanisation in flood-prone areas of Valencia have reduced its capacity to cope with intense rainfall, so any severe weather was more likely to create a disaster. With urbanisation comes an increase in the area of land that's covered with impervious man-made surfaces like concrete and tarmac. These materials are pretty poor at absorbing rainfall and lead to more surface runoff, which contributes to flooding. And although the flooding in Valencia was unprecedented, existing flood defences in the city were either outdated or badly managed. They simply weren't good enough to hold back the surging waters that coursed through the city. If this tells us anything, it's that Valencia is in desperate need of an update to its disaster management strategy. Since the Valencian people can't fully prevent the rise in severe weather without a global shift in the use of fossil fuels, their best option is to make sure that their preparedness, response and recovery are as effective as possible. If they don't make changes soon, the price is significant. More devastation that will be increasingly difficult to recover from. Although we've become more environmentally conscious in recent years, the reality is that we're still pretty reliant on fossil fuels. So until we can break free of this dependence, global warming and the unpredictable weather events it brings are likely to become more prevalent, even in areas that were previously unaffected. The Valencia floods are a prime example of this. It's important to understand how the storm may have been brought on or amplified by global warming. You might be shocked at how many of the storm's features can be linked back to climate change. First are the cut-off lows. Experts predict that cut-off lows will become more common with ongoing global warming because warmer temperatures make the jet stream weaker, slower and more meandering. If you remember, this is the recipe for producing cut-off lows or renegade cold drops, so they're likely to get more frequent and form in new areas across the globe. And the jet stream is not the only system getting weaker. In a phenomenon known as Arctic amplification, the poles are warming at a relatively faster rate than the rest of the globe, and this is destroying the temperature gradients that drive global circulation. Upper level winds are weakening as a result, and this is likely to make storms more slow moving on average. If this happens, Europe could see an increase in quasi-stationary storms like the one witnessed in Valencia. Warmer ocean temperatures mean that evaporation from the surface becomes more frequent and persists for longer throughout the year, fueling convective processes and bringing unseasonable weather patterns. The fact that the Valencia flooding could happen in late autumn is probably a sign that this is happening, and if this continues, then we can expect these storms to hit throughout the autumn months and well into the winter. Even if the oceans don't continue to warm, higher average air temperatures change the physical properties of the air itself, which is also not great news for us. Warm air can hold more moisture, so the risk of torrential rainfall is increasing. Any weather event interacts with the landscape, and it's this interaction which influences how bad the impact might be. If the weather is more unpredictable, this interaction is changed, making us more vulnerable to natural disasters. So it's likely that climate change could make existing flood management ineffective or even dangerous, especially when authorities have failed to predict its future impacts in target areas. One scheme in Valencia which might have fallen victim to this is the Turia River rerouting project. The Turia River is renowned for its flooding potential since it burst its banks in 1957 and brought devastation to the city centre of Valencia. In response, authorities developed Plan Sur, a scheme to divert the river southwards away from the city centre and to relieve the area of flood risk. In many ways, the project was a success, but these recent floods have led some people to question how informed experts were when planning the diversion. It seems that hydrological calculations made in the 50s and 60s when the project was ongoing didn't account for the increased precipitation caused by climate change. Without these considerations, the diverted river may not be able to cope with peak flow rates, turning what was once an asset into a liability for the floods in the 21st century. It can seem like an impossible task to prepare against something so changeable with the potential to cause so much damage, but we have to try. Luckily, there are some promising changes we could make that would help us be more resilient against climate change and the severe weather it causes. So what could the future look like for Valencia? The city will obviously have to rebuild in the worst hit areas, and this needs some innovative urban planning. The president of Spain's Higher Council of Architects and an expert on the topic of city redevelopment has emphasised the need for more permeable materials in urban design projects so that rain can be absorbed into underground stores rather than just running straight off the surface and causing floods. The recommendation is to return to the traditional compact Mediterranean city. So what would this look like? Well, picture geometric plans, green courtyards, permeable cobblestone streets and open piazzas. It might seem strange that an urban design from the past could be better at flood defence, but all these features are designed to make the most of natural materials, which are much better at absorbing water. And apart from flood defence, these design features are much more sociable for people living in these cities and provide lots of green spaces to benefit mental health. Okay, so modern is out and traditional Mediterranean is in. Good stuff. But what about the more specific flood defences that Valencia will need if it's hit by torrential rains again? Newer ideas like nature-based solutions could be really useful here, and Valencian authorities would be smart to utilise them more in their defence plans. Nature-based solutions are centred around the idea of working with nature, for nature, to address social, economic and environmental challenges. The great thing about this concept is that it can be applied in so many different ways. From rewilding to urban greening, these projects are all designed to benefit both nature and people. One example of where nature-based solutions have been used for flood management is with floodable parks like Engenhavenparken or Climate Park in Copenhagen. In the 2010s, the people of Copenhagen were also hit hard by flooding events, so they built Climate Park to try and adapt to the new reality of climate change in the 21st century. The park is cleverly located at the bottom of a hill and holds space for 9,000 cubic meters of rainwater, or 3.6 times the capacity of an Olympic swimming pool. In the event of extreme rain, automatic gates can rise around the perimeter of the park without needing any electricity, blocking entry to the public and storing even more excess rainwater. The park not only defends against extreme weather, but it also provides a social green space for visitors, adds aesthetic value to the city, and recycles any rainwater it stores for watering the plants. These design features were so successful that the park won a regional award in 2021 for its impressive contribution to the architectural landscape of Copenhagen. If Valencian authorities could incorporate an idea like this in their plans to recover from the October floods, then it could produce some really positive changes, not only for managing floods, but also for the well-being of the people and the sense of pride in the city. We are slowly but surely waking up to a new reality of severe weather in this age of global warming and changing climate. Whether it's the Valencia floods or the wildfires in Los Angeles we've seen, we can all think of a recent event that links back to climate change and to our reliance on fossil fuels. It's getting harder not to notice the things that are changing, especially for those countries that aren't used to severe weather and natural disasters like this one. We urgently need better strategies for coping with this new normal if we have any hope of protecting our livelihoods and those of the next generation. Although it's going to be a huge challenge for us to keep global warming under the current target of 1.5 degrees, there are things we are getting better at. We've never been more aware of the link between biodiversity and climate, and making positive changes for one will undoubtedly bring benefits for the other. Nature-based solutions are grounded in this idea, so if Valencia can include any of that in its rebuilding effort, then the city will hopefully be much better prepared and more resilient against any future severe weather threats. Looking back in its own history into cities like Copenhagen, well, that would be a great place to start. Whether it's protesters campaigning for a better response to the floods, or the climate debates that the flooding provoked, what happened in Valencia last year has definitely got us talking. The challenge is whether we can turn talk into action. This is what will truly bring closure for the victims of this disaster.